Welcome to the Educational Series Part 3 on how to control an inverted pendulum. If you still have not watched previous parts to understand how to derive and implement linear control on inverted pendulum, please go back and watch them. In this video, we are going to stabilize pendulum from any position using the desired energy method. In the previous part, we saw that linear controller, or LQR controller, can only stabilize the inverted pendulum when we start pretty close to our desired position of pointing up. And when we deviate too much, the system fails, leading to an uncontrollable motion. So we are going to use desired energy controller to bring the pendulum to the range close to our desired position. Within this range, we know that our linear controller can successfully stabilize the pendulum. So the second we enter that range, we will switch from the desired energy controller to the linear controller. First, let's look at the desired energy method. Our final goal is the pendulum pointing up without it moving at all. So the total energy is going to be equal to mg times 2L. However, our current energy state is not going to be equal to that. So our current state is going to be a combination of a potential and kinetic energies for the pendulum, and we get current energy is equal to mg times y position of the ball plus 1/2 m times ball velocity squared. And to make our current energy match the desired energy, we're going to apply force U to the cart, where U is going to be equal to negative k times the difference in energy states times the sign of our motion, clockwise or counterclockwise. In Matlab, we are limiting our force to the maximum of 70 newtons. You can optimize this value based on many factors, the main one being how much force you can actually supply. Another important consideration is that we do not want to move too fast when we enter our linear range. If we move too fast, we will just fly out of it without having a chance to stabilize it. As you could have noticed, our pendulum dynamics function is pretty much the same. The only thing we added was an if condition, saying if we are outside the range, we want to use the desired energy controller. Else we want to use our LQR controller setting reference at zeros, 0x, 0 velocity, 0 theta, and 0 angular velocity. To know if we are outside the range or inside the range, we need to create another function called an event function. This function triggers value to turn to 0 if we are within the range that we know we can stabilize using the linear controller. In our case, it is 0.5 radians. So we create a variable called options and use ODE_set to set the events to our custom event function. Then we pass this option into our ODE45 function along with time and initial condition. Please notice that we first check if we start within the 0.5 radian range. Once we reach 0.5 radians range, we will continue by running our pendulum dynamics with LQR option. Please notice that in here, we specify our initial condition as the last position from our desired energy controller. So if we comment out LQR portion of the dynamics, we can see that our simulation ends when it gets within the range. Then LQR picks it up from this position and runs the linear controller. This way, with a combination of the desired energy controller and Linear-Quadratic Regulator controllers, we can stabilize the pendulum from any position. Please note that if you build the system, you will require to tweak some of the parameters and maybe change the dissipated energy formula for the best results. On this note, this educational series are done. Please feel free to leave a comment, and I will do my best to answer all the questions. Thanks for watching, and good luck in your endeavors.